Lab updates for the week. Some of the 4060s left this week to a lucky viewer. I won't call you out, but thanks for supporting the channel. We had a blown power supply in the main node. This SiStar 1000 watt just wasn't up to the job of running 6A4500s. So, yeah, out it goes. In is the EVGA 1600 watt power supply. This is not for the bench node, this is for the main node in the server cabinet. So let's get that swapped out so that we can get to testing distributed inference. And welcome back to the lab, robots. I hope everyone's got their morning coffee or their relaxation technique with them. Today we are going to go through and take a look at some of the new technology that has been released basically from underlying pins like Llama.cpp. And the big thing that we're going to focus on is this distributed inference. So this is a huge thing for especially for folks like us who are running local labs to be able to run LLMs or AI. This basically is going to set up a server that could be federated even, so you could have multiple servers to be able to load balance requests to an OpenAI compatible API, such as LocalAI, which I am using here. You guys can go check out LocalAI at localai.io. This will run on pretty much anything. It has Docker containers to run on anything, multi-platform. You can make it run in Kubernetes like I do. For today's thing, I had to do some hacking around because the Helm charts for LocalAI isn't quite ready to be able to do distributed inference and deploy workers. So I just kind of built my own just to show you guys how this actually can work. And so that we can mimic having basically a server and a bunch of different nodes and do testing across it. I'm going to pause everyone right here. I want you to think about this for a second. When we're talking about this, this could lead to community-driven large pools of hardware for all of us to run multiple models or very large models across a network or across the internet. So this is something that they are working on in local AI right now, to have these global community pools to share the local AI federated instances and workers. This would be cool, guys. This is open source hardware, big giant clusters that we could make across the internet and do it. Next question I want to ask you guys, and go ahead and put your comments down below, is if we are going to look at this structure where we are going to have a main server and GPUs on this main server along with other nodes or other machines that have GPUs or don't have GPUs. Now I'll throw in this thing. This could be very cool for mixing different backends as CUDA or Metal or even ROCm across the board to be able to run different types of GPUs or different types of hardware, such as like the macOS and Metal, and put them in a cluster. So let's take a look at this. Like if we're using the network, and in my lab, I have a 10 gig network and 2.5 gigabit network and 1 gigabit network that are all kind of tied together. My main machine, my main big node that we talk about, does have 10 gigabit networking on it. The bench node that we use for testing most of our GPUs has 2.5 gigabit network on it. So I do have a faster network, I suppose, than most people might be running, but in the case of like designing systems like this, having 10 gig or 2.5 gig is definitely going to be a benefit. But now what I want to ask you guys is, if we look at this and I go run a test on just our normal thing of like, say, we'll use Llama 3.1 70B today, so a gigantic model, right? If I'm running this mainly on my own one node, and we get a certain amount of tokens per second, and then I spread that model across this node along with a few other workers or even just one other worker, what do you think is going to happen to our tokens per second? Go ahead, comment down below. Let's go ahead and find this out. So we're not going to do a ton of testing today. I'm going to try to make my screen larger for everyone to see. I do apologize. This is recorded on a 4K screen because we're trying to fit so much information in here. for you guys to see. I'll try to do my best here. Let's go ahead and run our baseline test. We need to figure out on a single host what this model at a certain context size, etc., is going to produce. And then we're going to spread that out. We're going to bring some workers into this cluster and see how well it does. Let's go ahead and get to it. I'm going to go ahead and remind you guys while we're here that this distributed inference is built into LocalAI. You can host LocalAI. It does have its own chat. It does have its own ability to generate images and text to speech and everything else that you want to do. Just go read the documentation. This will run on anything, especially if you're just using Docker. This is a great project and I'm a huge fan of it, and obviously you guys see me doing it all over the place. I do build all of my apps to use a LocalAI API endpoint compared to just using the chat system in here because I like having the API endpoint. All right, let's hop over. Today we're going to be using Meta Llama 3.1 70B Instruct Q5KM. In this case, we're going to run about I think that is a 56K context size. The reason why is this will fill up my main node basically. And my main node has 6 20 gig A4500s in it. And we're going to do some just baseline testing with that just to make sure that this works. We're going to go ahead and hop over to our test. We have the main node up. You see that we've got just our typical 6 A4500s in here. We have the Meta Llama 3.1 70B Instruct Q5, right? And if we go take a look at the Q5 models, the Q5KM in flat files is about 50 gigs flat files. Now remember, Meta Llama 3.1 increased its context size all the way up to 128K. So that will take a dramatic amount of VRAM. Today we are only going to run it with 56K just to do some comparison across the board. So let's go ahead and kick this into action and we will go and take some look at all of this. Let's do a L3.1-70B Q5 KM 6 times A4500. And I am not going to skip the first result here because we want to see just how long that first result took to load up the model locally on this node compared to doing distributed inference on the next test. So let's go ahead and leave that the way it is. We're going to do our typical 20 tests. And remember, we are going to use a static 100 token prompt that basically asks the AI to go ahead and build us a Docker or a GitHub action that will build a Docker container and push it and do a few other things. It's just exactly 100 tokens so that our test over and over and over, we're sending it the same exact prompt. I am not setting a seed on here to try to get the same results. I am not caching any prompt results. I am not doing anything of the sort so that this works across the board as hopefully a fairly static test for us. Let's go ahead and get this kicked in. Because we're trying to look at so much info today, I'm going to make the screens much larger and we'll pop through some screens just to see how things look. At the very top on this side, we have NV top. This is going to be live metrics that are watching this node so that we can see how much the memory is loading up, how long it's taking the nodes to run, the CPU, and the memory percentage. Over here, this is Grafana and Prometheus, and specifically the NVIDIA DCGM exporter that runs in my Kubernetes cluster. Right now, we are watching the node that has those 6 A4500s in it, just so that we can go ahead and get an idea of what this is going to take. These metrics will lag behind our live test over here, so just remember that, but it'll give us kind of a more of a visual. Looks like the model has gone ahead and loaded up. Let's go ahead and get a feel for what Meta Llama 3.1 70B feels across 6 A4500s. It's looking pretty good to me. Moving pretty decently. Hopefully you guys can see this a little bit better, especially if you're on a smaller screen now. And we can see that it's pretty much filled up that 120 gigs across those 6 A4500s. And it's going pretty decently. Remember, this is a really big model with a very high context level. We're not using that context right now totally, but we do have it set so that it sets that VRAM. So we can see if we go over here now, in total, it looks like we're running about 113 gigabytes of VRAM across all of those A4500s. Now let's pay attention and we'll see how this goes as this kick in and level off. All right, 113 gigabytes. In total, using about 570 watts. I think that's going to go up a little bit. And since this is the A4500s, we can see the PCIe traffic going across the board. So you can see it coming in and out of those cards as they transfer data across the PCIe. Now, I want you to remember that because it's doing that across the video cards. When we go into actually doing distributed and adding workers in here, it's going to do it across the network. So how much slower is that going to make things? And what do you guys expect? All right. Looks like we're averaging so far just about 9 tokens per second. I assume through our runs here that will sink down to about, 8 tokens per second. All right, well, let's go ahead and let our baseline run. I'll pull up some of these metrics for you guys to watch, and we'll go into fast forward mode. Wow, I hope my microphone picked that up. That was just a set of jets flying over my house. All right, I'm going to squeeze this over so that you guys can just watch the metrics over there quite a bit more. And we'll let this go. Okay, that report is over. I hope everyone could see the metrics a little bit better this time. And let's go ahead and produce this report. I'm going to grab the name real quick so I can reuse it. But it did look like it fell down to about 8 tokens per second, which was kind of expected. I mean, this is Llama 3.1 70B. This is a really big model. Let's go double check our data. Just make sure everything looks good. Back over so that we can see it. Show the raw data just so I can double check it. Make sure we've got no zeros across the boards. Yeah, it looks pretty good. Okay, so we didn't skip that first one because we wanted to see like that first prompt eval time, like how long it took basically to load up. Remember, these models on this particular node are stored on an NVMe drive, so they're pretty quick. But we're going to want that to compare to the distributed over the network. Let's go ahead and just take a peek at our evaluation tokens per second, just because that's what we're all going to go off of, and this is mainly our baseline. So it looks like we fell down to just over 8 tokens per second. That seems about right. And we'll go ahead and leave this, and we'll talk first about what we're about to do. With this technology, which is right in my wheelhouse of running clustered anything really, and that's what I like to do, is remember that we're going to have this one, or our main local AI instance, which is running Llama.cpp under the hood. Let's go take a look at our swarm page, right? We're doing distributed inference. Don't worry about that up there. That's because I'm running this as a container, and I restart the container and it re-shows up because there's two running at a time for a short amount of time. Now, federated ones could make it so that you could load balance requests across multiple different servers, which could come in really handy if, like, say, you're trying to run Llama 3.1 8B, but you want to be able to serve thousands of requests. That might be the easiest way to do that. The big thing that we want to look into today, though, that's going to interest everyone is going to be the workers portion. This allows you to use other Llama.cpp workers, specifically over RPC, to distribute the weights between the workers and offload some of the computation. To start a new worker, we would basically be starting up LocalAI, whether on your local machine or through a Docker container, or in my case, in Kubernetes, with this token that we're going to export. Don't worry, I'm going to copy or change out this token when I'm done. This is just for this demo today. But we're going to start it up as a worker, and underneath the hood, there is different ways that it connects, which is basically MDNS, and then there's also a VPN tunnel system that they set up in between the Federation nodes. You can read more into it. I still need to learn more. I'm just showing you guys as I'm playing around and having fun. So what I did instead is I went and built some Kubernetes deployments that will specifically deploy workers with this command and this token to start it up. To show you guys basically what we're talking about here, I'm going to open up a new window. Give me just a second here, folks. All right, let me try to make this bigger for everyone. So we're connected to one of my Kubernetes clusters, specifically the one that has our two different GPU nodes in it. Our main node, the GPU node that has the 6 A4500s in it, is in a different namespace. It's a totally different node, right? You can see that here. Let me pull this back up. Remember, this is NV top. So this is the GPU node. It's got the 6 A4500s in it. The bench node that we normally use for testing right now has 3 4060s in it and a 3090 in it. In this case, just for this demo, I have split those video cards up to 4 different deployments so that we could mimic having 4 Llama.cpp workers added in to our main server and spread that load even more across. If we look at this, that 3090, right, is device 2, so it's actually going to be LocalAI worker 3. All I'm going to do is I'm going to scale this deployment and bring in a container. So this would act like another machine on my network. It actually does. It's another container on my network. But say you wanted to use your kids' gaming machine and use their video cards to extend it, you could just go run this container on their machines or copy down the LocalAI GitHub repo and launch LocalAI with that token and the worker command, and it would start broadcasting on your network. So if you guys were paying attention, as soon as this came live, we added in a new worker down here. So this worker has a 3090 in it. So that card, the 3090, is actually slightly faster than the A4500s. It's in a container in Kubernetes running on a completely different node that has 2.5 gig network in it. The main node, the main server, has 10 gigabit networking in it. What do you guys think is about to happen when we add this 3090 from a totally different machine over a network into this? Put your comments down below. Let's go take a look and do exactly that. So we have one worker up here. We're going to go back to our testing. We're going to flip back over to our main GPU node because this is the one that is in federated and has the worker attached to it. We're going to run that same exact test with the same exact model at the same context. It's just going to make less VRAM per video card, and it's going to spread out across the network automatically. So let's make sure we get the right model. I'm going to paste in that and add a dash distrib 3090. And again, we are not going to skip this first result because we kind of want to see how much longer it's going to take to run and or take to load the model up over the network. So let's go ahead and get this started. And I want you guys to specifically watch NV top over here to start. And notice that on that other machine, we already have a Llama.cpp RPC server running, and it's just sitting there waiting for work. So what we're going to do is we're going to cycle this pod to clear out any results and to clear out this memory. And the distribution only works per one model right now, and it only works if those workers are already in there when you start the inference. So we're just going to cycle that, get everything set back up. We'll see the memory drop off over here. Hope you guys are actually enjoying this. To me, this is going to be amazing technology. All right, so we're right back to where we were. We've got a fresh setup. Let's go ahead and reload our P2P page and make sure everything is setting up. All right, we've got our worker showing on. Let's go back and start this test. So the first thing you should notice is it start to load up over here on the main GPU node, and then automatically you see it already spitting information over to this node. See how the memory on the GPU is already climbing? See that? Now I'm going to give you guys another look at this. This is the current traffic, and let's go ahead and put it back to 5 minutes that is going out and into the namespace where that worker node is, not where the main one is. So you can take a look here. You can see it's still spreading the model out, or the weights out in between the GPUs across the network. So it's definitely taking a lot longer to load up, but that is as expected. Once the model is loaded up, you're not going to be dealing nearly as much network traffic. And this is a big model. Remember, at least even flat files, it's 50 plus gigs or just at 50 gigs. And remember, these metrics will lag behind a little bit. We'll go ahead, and while that's still loading up, let's go reset up our page here. Because this time we're going to want all of our nodes so that we can watch all of the GPUs, even though we're not going to use all the GPUs. We're only going to use the 3090 from that other node this time. You can see that cranking up. Let's flip over and take a look at the main server deployment. And you can see that it's definitely cranking up on transmitting the data out. And the data coming in. Still hasn't quite started. Let's see where we're at. All right, there it goes. We have, it looks like 18 to 19 gigabytes on that 3090. Do you see that, guys? And the rest over here on the A4500. So two different nodes. Let's take a look about how it feels. That doesn't feel too bad to me, guys. That's also across the network, remember? How does this feel compared to the test where we were running everything on the same exact node? You can see we're clearly using the 3090 over here. Not a ton, but it's spread out and it's not using a ton of CPU and stuff over here either, but just using a lot of all the VRAM. Really doesn't feel too bad to me. It looks like the top one, or first one, came back at about 8.3 tokens per second after loading. Not bad. This should be catching up over here now. Yep, a little bit more VRAM usage because we're showing all of the nodes, right? It's definitely going to be more power usage because that 3090 is pretty power hungry. And I'm not power limiting anything right now. Probably a mistake in how I blew up that other power supply, but you know, it goes. Seems to be running pretty decent. For distributed inference over the network, 8 tokens per second. I mean, this is pretty much where the other one on a single node fell to. So I would expect that this will fall to maybe 7 tokens per second. Isn't that amazing, guys, over the network? But let's find out. We'll go ahead and shrink this down a bit and let that run. And again, just before we go into fast forward mode for this, I'm going to show you guys that this was adding just one 3090 in. And if I show the logs on this, oh, you won't see it because we're way past that already. But you guys can see over here on this one, it is clearly split in between one node and the other node through a single server. Okay, let's let this go into fast forward mode and we'll come back at the end and compare what we've got in distributed inference. Pretty cool, guys, pretty cool. Wow, I'm in awe. The future of this technology is going to be amazing. I will just put it that way. We finished off here with about 7 tokens per second in a distributed mode. So that was using my network in between 2 different nodes here, and the combination in total of 7 GPUs, 6 on one on the other. That's pretty impressive. Normally I try to retain my excitement or my professional opinion because I am not a professional at this. However, I can see where this leads to. Global communities, global pools of resources, and let's take this even farther. So let's say you've got a ton of kids. You got 3 or 4 of them out there, and they all have 4060s in their machines. They're not home during the day, and you want to use their machines to run AI. Let's go ahead and bring in 3 more nodes into our swarm and see how it goes. First, let's go ahead and produce this report. Grab this name so I can reuse it again. All right. Let's go ahead and expand out and go take a look. Make sure that report looks good. 3.1, 3.1. Distributed. All right. Much longer to load, if you remember, but we would expect that since it's using a network and not direct NVMe drives. Data looks okay. Let's hop over and see what our final evaluation tokens per second was. Just over 7. So one node with 6 GPUs was just over 8. This is 2 different nodes on the network, just over 7. If you made a comment below before about your guess and you were way off, or even if you weren't, go update your comment now and let me know if you're actually surprised after seeing these results. All right, let's go do that one last test. Let's take this to a little bit more of an extreme. So what I want to do now is each one of these is going to act like another one of my kids' machines in my network, and they each have a 16 gig 4060 in them. I'm going to go to their machine and I'm going to start up this container because most people aren't running Kubernetes clusters in their house with GPU nodes. We're going to go ahead and spin up all of these. And we will let them all turn on. I'm going to get this off the screen and out of the way. We are going to go back to our main GPU node, and we're going to cycle the pod just to clear all the logs out so we get good results. Okay. And now let's go check our dashboard. And now we've got 4 workers to add into the pool. So we've got not only our original federated instance server with those 6 A4500s, but we've got a node with a 3090 in it, and then we've got 3 nodes with 4060s in them. All right, so we've got this whole swarm of Llama.cpp workers now, and a server in front of them. Let's go back. We're going to take that same exact Llama 3.1 70B Q5 model. And remember, we won't see all the other GPUs here because they're in a totally different node. We're going to paste in our name and add 3 4060s to it. We're not going to skip that first result again. And then we're just going to go ahead and go for our typical 20 tests. This time we're going to be using all 10 GPUs that are in the lab. So let's go ahead and hit send. And I'm going to flip back over to NVTop across the 2 nodes so that you guys can see. This time we've got 4 workers on this node, right? So this is mimicking 4 different nodes. You know, this is, Harry, Bob, Sal, and Jim's machines with 4060s in it. Their kids, they're off to school. Don't worry about it at all. We can see the memory loading up across all of those machines, including the main node over here. Again, this is doing it over the network. So this is going to take a little bit. Let's sit here and watch. You guys can watch the VRAM usage increase across all the nodes. And I'm just giving you guys like what a real life feeling would be of watching, a 70B model load up across the main server and 4 nodes. Normally, if you're running a distributed system like this, that model would be preloaded. So you wouldn't be actually sitting here waiting for it. But in the case of labs and stuff like that, let's see how long it takes, because this is over the network and makes this quite interesting. Should we go ahead and take a look too at the panel while we wait for that to load up? Let's expand that out just a hair. These will lag behind, right, these metrics, so we're going to wait for them all to pick up over there. And in reality, it's not sucking that much bandwidth. As we saw before in the test, the regular bandwidth is not that high, but I want you guys to pay attention and tell me what you think. All right. Still transferring all the data around. Yep, that's a decent amount of bandwidth. But not terrible. Not terrible at all. You can see it's still working it out. Say we should get a reply any second now, any second. Now remember too, the 4060s that we just added in are even a lower performing card, right, than the A4500s, right? The 3090 was actually a higher performing card, but we still got less tokens as we would expect. Now we added in not just the 3090, but 3 of those 4060s on 3 different nodes. There we go. We got the memory all up across the board. Take a quick look back at the network. This first one sure is slow, but once it's loaded up, it starts rocking. And I did do some playing around earlier with a smaller model, and it obviously goes much quicker when you're copying it across the network in a case like this. But still fairly impressive. Okay, we can see the individual nodes down there going to a little bit of work. Come on, swarm. All right. And there it goes. Now remember, as this goes along, this is a swarm made up of 5 machines. Or at least pretending to be 5 machines. And adding in those 4060s is definitely going to slow this down a little bit too. But we're running inference technically across 5 different machines right now, if you want to think about it that way. Not too shabby, not too shabby, guys. Not too shabby at all. 405B is not a dream when you think about distributed. And you don't have to do this just for GPUs. You could do this with CPUs and RAM. And this technology is brand new. So we just have to wait for it to get even better than what it is. And at the rate that things move, wow, I'm impressed. So the first one is back at about 5 tokens per second. So I assume as this falls and settles down, we'll look at about 4 tokens per second across 4 machines and multitudes of different video cards. This is a 70 billion parameter model, so it is not going to be the fastest thing on the planet. But this is really, for me, this is amazing. I'm excited about what the future holds here. And there you guys can see some of the network consumption that's going on while this is running the inference. Just another way for folks at home to run giant models with huge context numbers. And also a way for enterprises to build highly resilient LLM API systems with clustered workers. All right, what do you guys think? Let's set it up and let this test run. We'll come back at the end, pull all of this information together, and check out what it looks like. See you guys in just a bit. All right, finished up with that test. Settled down to about 4 tokens per second once we added in those 4060s. To be clear, I think if you take a set of like 4 4060s and run Llama 3.1 70B Q5 on it, you're probably only going to get about 6, maybe 5 to 6 tokens per second. So this is not bad at all, considering this is distributed inference across 5 machines using 10 different GPUs. What do you guys think? Do you want to go add to your comment? Let's produce this last report. Go take a look at the data, and then we'll squash all these reports together so that we can really look at things. Also, did you guys notice about 750 plus watts across the board? Not too terrible. Not too terrible. All right, GPU report 3.1. That's not it. Oh, there it is. I'm being dumb. Okay. So load time, much farther up there. Again, we had to do it across more nodes. All right. Let's just check my raw data before we go any farther. Looks good. Let's hop over and take a look at the evaluation tokens per second. So just under 4 once we brought in those extra nodes with the 4060s in there. Okay, let's go ahead and bring this all together. There is just the A4500s. There's adding the 3090, and there's the final one with all 4 nodes in there. Let's combine those files. And now let's go take a look at the combined results and see where we're at. So throughout these tests, let's take a look. Just the single node with the 6 A4500s is going to be in blue. Once we went to distributed inference and added in that single machine with just a 3090, that's going to be in orange, and then green is our final test with basically the server and the 4 different nodes. So we can see the different load times basically across the board, how long it took to basically respond or get going on that first one. This would be as expected. I wouldn't expect anything else, but once it gets going, it'll flatline out. So let's take a look at the evaluation time. Green at the top, once we added in those 4060s, remember this was probably going to run about where your slowest cards would be, maybe a little bit better, but this is also network-based inference. So there you guys go. Total time should basically mimic that. Prompt tokens evaluated should be 100 across the board since we run a static test there. Completion tokens, this is going to vary depending on the length of the response. Total tokens should mirror that. Prompt tokens per second. Okay. There we go, as expected. You know, the local machine is definitely going to go faster, but this is not bad at all. This is not bad at all. And then the final thing everyone wants to see is the evaluation tokens per second. All right, so we started off with a single node with 6 A4500s in it, and it averaged at the end about 8 tokens per second. Once we went to distributed, so adding in a network-based node that had a 3090 in it along with the 4500s, look at that, about 7 tokens per second. Now we go even farther with that distribution, right? And we add in 3 more nodes that each have 4060s in them and come down to about 4 tokens per second. All right. Anyone want to amend their comment again? Tell me what you guys learned from this. I'm really interested in where this is going, and I'm very interested to hear where you guys think distributed inference is going. What'd you learn? Tell us. And just remember, this is not a how-to video. If you guys want me doing how-to videos, they would be much longer, and I'm happy to do those and show you how I set all of this stuff up. But I think the data videos are more than long enough for everyone at the moment. Most people don't watch hardly any of them. They just watch for the results, which I don't blame you. Next up, I want to say thanks to everyone. It looks like we hit 500 subscribers in this last week, which is just absolutely amazing. You guys are all just as nuts as I am. I'm kind of curious with all these GPUs and the heat they produce, if I can cook a pizza on the GPUs. AI, can I cook a pizza on the GPUs? Let's figure that out. Hope everyone had a good time. We'll see you next time.